This lecture is going to be over section 25.2. We're going to be discussing the eye. Now, within the eye, you can see here that we've got rays that are coming in, and then the lens is going to be focusing or changing, bending those light rays until it hits a spot back here. The spot along the retina is going to be used in order to be able to create the image. So a real image is going to be formed on the retina and transmitted to the optic nerve. Adjustments for various object distances are made by the ciliary muscle. For close vision, the lens becomes more convex, decreasing its focal length. For sharp vision, the image must be formed exactly on the retina. In the nearsighted, myopic eye, the image is formed in front of the retina. In a farsighted or hyperopic eye, the image is formed behind the retina. The power of the corrective lens and diopters is the reciprocal of the focal length in meters. So the essential parts of the human eye, considered the optical system, are presented here. Have an object out here. It comes through the pupil, the iris that surrounds the pupil, and it hits this crystalline lens. And you can see the ciliary muscle here trying to adjust the lens itself. And so if it's a contraction of that ciliary muscle, it causes the lens to become more convex, decreasing its focal length to allow for near vision. So you've got the vitreous humor out here, you've got the aqueous humor here, and then the image is formed in here, and the retina lies along the back of the eyeball. And then leading from that is the optic nerve. So the eye is nearly spherical and about 2.5 cm in diameter. The front portion is somewhat more sharply curved and is covered by a tough, transparent membrane called the cornea. The region behind the cornea contains a liquid called the aqueous humor. Next comes in the crystalline lens, and then a capsule containing a fibrous jelly, hard to the center, and progressively softer at the outer portions. And the crystalline lens is held in place by ligaments that attach to the ciliary muscle, which encircles it. Behind the lens, you see the eye is filled with a thin, watery jelly called the vitreous humor. The indices of refraction of both the aqueous and the vitreous humors are nearly equal to that of water, about 1.336. The crystalline lens, although not homogeneous, has an average index of refraction of 1.437. It's not very different from the indices of the aqueous and vitreous humors. Most of the bending light rays enter the eye at the outer surface of the cornea. You probably wouldn't want that much of a difference there because you don't want too much refraction going on. So that's why they're fairly close in values. So you can see a diagram there of the rods and cones along the human eye. So refraction at the cornea and the surfaces of the lens produces a real image of the object being viewed. The image is formed on the light-sensitive retina that lines the rear inner surface of the eye. The retina plays the same role as the charge couple device in a camera. The rods and cones in the retina act like an array of photocells, sensing the image and transmitting it via the optic nerve to the brain. Vision is most acute at a small central region called the Fovea Centralis, about 1/4 of a millimeter in diameter, which is pretty small. In the front of the lens is the iris, and this structure contains an aperture with variable diameter called the pupil, and that opens and closes to adapt to changing light intensity. The receptors of the retina also change their sensitivity in response to light intensity. So for an object to be seen sharply, it's got to fall right on the retina The lens to retina distance corresponding to S prime does not change, but the eye accommodates to different object distances S by changing the focal length of its lens. When the ciliary muscle surrounds the lens contracts, the lens bulges and the radii of curvature of its surfaces decrease, thereby decreasing the focal length. So for the normal eye, an object at infinity is sharply focused when the ciliary muscle is relaxed. With increasing tension, the focal length decreases to permit sharp imaging on the retina of close objects. So you can see here there are certain defects within the eye. This is what a normal eye would look like. The rays come in and they focus on the retina. If you have nearsighted eyes, what happens is that the rays focus in front of the retina. If you have hyperopic or farsighted, they are focused behind the retina. Astigmatism refers to a defect in which the surface of the cornea is not spherical, but is more sharply curved in one plane than another. So the horizontal lines may be imaged in a different plane from vertical lines, and that may make it impossible to focus clearly on the horizontal and vertical bars of a window at the same time. So you can see here the shape of the eyeball causes vertical and horizontal elements to focus at different distances, which is what's going on back here. This cylindrical lens is curved in the vertical, but not in the horizontal direction, and this changes the focal length of the vertical elements. So farsighted people have trouble focusing on nearby objects. A converging lens creates a virtual image at or beyond the eye's near point. So in other words, as this comes in, you've got a virtual image out here, and the image focused on the retina is what you would end up seeing here. So an uncorrected or nearsighted myopic eye, again, that the light rays converge here off of the retina and inside the eye. So nearsighted people have trouble seeing distant objects, and a diverging lens creates a virtual image that is inside the eye's far point. So you got some exercises there that you can look at in some tutorial sessions. That would be good as well.